Okay, welcome to Congruent and Similar Solids with Mr. Hunt. Let's discuss what congruent solids are. Solids are three-dimensional shapes. Congruent, same shape and size. So congruent solids that are exactly the same size and shape. Whereas similar solids, we know what similar means. Okay, they have exactly the same shape, but not, so I'm just filling in the blanks here, but not necessarily the same size. Right. All corresponding dimensions of them are proportional. Remember that word. So there's a scale factor, if they're similar, going from one to the other. Basically, we're just generalizing what we know about similarity into 3 dimensions for similar 3-dimensional shapes. Before we go into some examples, let's look at a few figures that are always similar. So always similar. First one is circles. Okay, you have that circle and you have this circle. Well, what's the only changing part about them is the radius. Okay, this one might be 2, that one might be 5. There's a scale factor 2/5. Okay, that's the only thing that's changing is the radius. Similar to that, square. Any 2 squares are always similar. 2, 2, maybe 5, 5. Scale factor of 5. Let's see if I can fit in here. Cube and sphere are the other two, kind of the 3D versions of those two. Cube and sphere. So I mean, 2 cubes. 2, 2, 2, 5, 5, 5. The scale factor is 5. Or sorry, 2/5. 2 to 5 still. Or sphere, similar ideas as the circle. Okay. Let's look at some examples. So before we look at the example on your page, let's look at an example from 2 dimensions. I have 2 rectangles. The scale factor, they're similar because the scale factor between them is 1/3. 4/12, 2/6, going to be 1/3. Well, let's compare their perimeters and areas. Hopefully this will give us a glimpse into what's going to happen with 3D shapes. Okay, well, perimeter, this one over here, if I put down 4 and 2 there and 12 and 6 here, this perimeter is going to be 10. This perimeter is going to be 24, 36. Oh, excuse me, 12. Oh. 8, 10, 12. Makes a big difference coming up here. Okay, so let's get back to this. There we go. Oh, and 12. Okay. So let's find the area now, and then let's see if we can make some conclusions. Area 4 times 2 is 8. Area here, 6 times 12. Let's see, 72. So guys, the pattern all goes back to this scale factor, right? How do you get from 12 to 36? You multiply by 3. How do you get from 8 to 72? You multiply by 9, right? Well, how are we getting those numbers? Where do those come from, okay? It all goes back to the scale factor. The scale factor is either 1/3 from here to here, it's 1/3 if you're going from this figure to this one, or it's 3 going from this figure to this one, right? So it's 1/3 going this way or 3 going this way. Well, since the scale factor, okay, I'll write 3, was 3 going from the left to the right, well, the perimeter you just multiply perimeter by the scale factor. So I didn't even have to compute this one. I just know it's going to be times 3. This one over here times 9. How do we get 9? The area was 9 times. Well, scale factor 3 squared. You know what? You can always think of it's always going to be around the area is squared units. Perimeter is not, just times 3. Volume, we're going to see in a second, is cube units. So if there was a volume of something we need to find, it would have been this scale factor cube. That's what we're going to see in the next example. Okay, so I'm thinking about the on your own example here. In example 1, are the solids similar? Let's look at that really quick. Are the solids similar? If so, state the scale factor. Well, same as what we did in that example before. Compare all the ratios of the figures that match up. 20/8, 15/6, 5/2. Are those all the same? If they are, then it's going to be yes, they are. It's 5/2, or 2.5. So yes, they're similar because all of them have this same scale factor. If one of them is different, they would not be. All right, let's look at the on your own. Okay, so what we have first is it says determine the scale factor between the two prisms. Okay, we did that. It was 2/5 or 5/2, depending on which way you're going. I was going to go 2/5 this time, so it doesn't matter 2/5, 5/2. Just got to stay consistent. Okay, now determine the surface area and then the volume of each prism, and then we're going to write their ratios. Okay, so go ahead and do that. Pause the video, find the surface area and volume of each prism using the formulas. Okay, here's what you should have found for the myself more room for the big prism, and then I'll put small over here. Okay, surface area for the big one is going to be 950, and surface area for the small one is going to be 152. Volume for the big one is 1500. Volume for the small one, 96. So let's write the surface area and volume ratios between the two figures. And again, it doesn't matter which way you go. 950 to 152, 152 to 950, not going to matter. But I went small to big up here, so I'm going to go 152 to 950. Okay. And over here, volume 96 to 1500. Now, simplify those fractions. Hopefully your calculator can do that. You're going to get 4 25ths, and you're going to get 8 1/25ths. So maybe we're starting to see a pattern with these numbers. It goes back to the last example. Scale factor, perimeter, it's just going to have the same ratio, 2/5. But what do I do in that level? Back here, right? If it's area units, to get from, I'm looking down here. Oh, there we go, here to here. You take the scale factor and square it, and for volume, we're going to take the scale factor and cube it. So actually, guys, what we could have done on this one, we didn't know I wanted you to discover this, but we could have taken this 2/5 and said, hey, I know the ratio of the surface area. I'm going to take that, and I'm going to square each number. 2 squared is 4, 5 squared, 25. That's the ratio. Volume, cube each number. This is 5. 2 cubed, 2 times 2 times 2 is 8. 5 cubed is 125. Now, what we're going to do next is use this knowledge to solve problems for missing surface areas and volumes. Okay, so you can look at that theorem there. It summarizes what we just said there. Scale factor of two similar solids, if it's A to B, so if it's 2 to 5, the ratio of the areas, you square that. Okay, so A squared to B squared. That's what we did when we squared these. And then volume ratio, you cube them. Okay, so let's try some examples. So example 2, you have 2 cubes. They have side lengths of 9 and 21. Now it's cubes, they're all going to be the same. If you want to make a picture, you can. 9, 9, 9. A bigger one with, 21 for all of these. Find the ratio of the volumes. Well, here's what you got to do. I'm going to make this little chart. If you know A to B, the scale factor, A to B means the scale factor ratio. You can immediately find this is the ratio of the surface areas, and this is the ratio of the volumes. So you can immediately find the other two if you have the scale factor one. That's what you always need to work towards in these problems. So if we have 2 cubes with side lengths of 9 and 21, well, I know that the ratio is, for A to B, is 9 to 21. Guys, you can write this as a fraction too, right? 9 colon 21 is the same as 9 over 21. Okay, by the way, on this one, you could also reduce these fractions, right? This is divided by 3, it's 3/7. So either way, what's the ratio of the volumes? Well, we don't even need anything else. We don't need to compute the actual volumes. We could. This one's not too bad, right? We do 9 cubed up here and 21 cubed up here, and then we do the ratio. But all we got to do, that's actually what we're doing in this one, is I look back here at this, it's cubed for the ratio of the volumes if I have the scale factor. So I cube each of those, and I get 729 down here in volume ratio to 9261. If you simplify that fraction, it's going to be 27 to 343. That's the simplest form. Or you can write it in this form. Now, if we had just simplified this first and done 3/7, then it would have been a little easier. Cube at 3 cubed is 27 down here, and not 7 cubed is 343. So usually good to reduce first. Okay, let's try a couple more. Oh, by the way, in the last example, they were cubes. Because of that, we automatically know any two cubes are similar. That's why we could apply the theorem that we did. Okay, and did the ratios. All right, so let's use this now. We have two similar prisms. We're told they're similar, so that's good. We have the surface areas of each. What you do is you go to, okay, this is area. Remember, this is scale factor, the first row, and this is volume. You go to what you have. We have the surface area ratio, 144 to 324. What did I always say to go to first? If you know the scale factor here, you can always get whatever else you need. This question says, find the scale factor. Okay, we're going to use that to get volumes and stuff later, but all we need to do is get back to scale factor. Say to yourself, if you have something that's squared, right? I'm going a squared to a, b squared to b. What would you do to get back there? You're not going to divide by divide by 2, excuse me, or even divide by a. We shouldn't do that. Fraction of it. No, we're going to do a square root. So do a square root of these numbers, and the scale factor is 12 to 18. Let's always write in simplest form. I can divide a 6 into each of these and get 2/3. Okay. By the way, again, we could have actually simplified this first. Okay, and it would have worked, but I chose this to simplify later. Okay, last two. Okay, we're given two, in example 4, the surface area of two similar figures is given. So we don't even know what the figures are, but we do know that they're similar. Okay, so that's important. The volume of the larger figure is given. Find the volume of the smaller figure. We'll state the scale factor along the way. So we're given two surface areas and one volume. Well, write down what we have. We have area. This is area ratios. So write down what we have. It's 6 to 294. What did I say first? Always go to your scale factor. Then we'll be able to get to volume. Guys, there's no good way to get to the volume ratio from area. Okay. There is, but it's just easier to do it this way. So let's go to our scale factor. I'm going back this way. Okay. Now, square root of 6, that's what I'm going to do, right? Square root. I don't like that. Okay, it will work. You'll get a, decimal, blah, blah, blah. I don't really want to keep it like that. So let's go ahead and we can reduce this. 6 goes into 6 once, and it goes into 294 49 times. Now when I do the square root, this is going to work out better. Square root of 1 is 1, and square root of 49 is 7. So that's the scale, I'm up here in this row. That's the scale factor ratio. Okay. Now, where do I want to go though? I want to find something about the volumes. So let's go to volume. I'm going to go down here now. You say to yourself, how do I get from just a regular scale factor, A to B, to A cubed, B cubed? A to A cubed, B to B cubed. You cube these. So I'm going down here now. This will give me 1 cubed is 1, 7 cubed, 343. That is the ratio of the volumes. Now here's what's going to be new. We're going to use this to solve a problem. So what I'm going to do, I'm going to write that ratio. So this is a volume ratio. I'll put right here, 1 to 343. I'm going to make a proportion. All right? So that's the volume. This is going to be the actual. Well, what do I know the actual volumes are? Well, I'm given 3430. Guys, read the question. That is the volume of the larger figure is given. So that has to go down here, 3430. The question says, what is the volume of the smaller figure? So let's just call it x. All right, this ended up being my small figure in this row and my big figure in this row. Okay, so we're back to similarity, proportions, cross multiply. 343x equals 1 times 3430 is 3430. Divide by 343. We get 10. So that's the volume of the smaller figure. Okay, we'll finish up real quick. I'm going to go a little quicker through this one. Same type of idea as before, but instead of two surface areas and a volume I give you, This time I give you 2 volumes and 1 surface area, and say, find the other surface area. There's similar figures. This is my scale factor, area, and by the way, area or surface area, any type of area. Okay, so what do we know? We know the 2 volumes, so let's write that in. 6 to 384. Again, could get back to scale. We're going to scale factor, right? Always go there first. Could go ahead and do that, but let's reduce these. Divide each of them by 6. It's going to be 1 and 64. Okay, now ask yourself, how do you get from something a cubed to a? Well, in the last example, going from a to a cubed, we cubed it. Going now from a cubed to a, we're going to cube root it. So if we cube root everything here, that'll get us back to our scale factor, a to b. Cube root of 1 is 1. And again, find that math cube root button in your calculator. Cube root of 64 is 4. That's the scale factor. We want to know something about the area, so then I'm going to take these, I'm going to go to my area. Alright, so we're going to go here. We are going to, from a to a squared, we need to square these values to get down there. So 1 squared is 1, and 4 squared is 16. That's the ratio of the surface areas. We now use that to solve a problem. So I'll write the ratio, right, 1 over 16. Then a proportion, well, what's the actual? Now, what are we given here? The surface area of the smaller figure is given. So that's going to, I don't know if I discussed it well enough in the last one. Well, where does that go? Well, 1 is the smaller number, so I need to put 6, the given surface area, with 1. And then 16 is the larger number, so I'll put x down here. This is the one we're trying to find. Okay, then we cross multiply, it's x, and then here it's 96. This time it's squared centimeters. Thanks for watching, and enjoy learning about congruent and similar solids.